Hi there, this is Stephen from EDRMedeso UK. In this short tip and trick video, we're going to talk through a simple tutorial demonstration of the melting solidification model in Ansys Fluent. So the physical problem that we're going to look at is quite simple here. It's actually a 2D problem, so you can run through this very quickly in your own time. We have an annular disk here, and we have an inner boundary, and this is going to be heated to a constant temperature. The outer boundary we'll assume is adiabatic, so zero heat flux. Now within the annular disk we're going to have a phase change material, or PCM, and this is going to be wax, and this is initially going to be in the solid state. And as we run the simulation, what we're looking for is the liquid front starting from the heated boundary and moving radially outwards. So that's the basics of the engineering problem that we're solving. We'll just talk through the setup in Ansys Fluent. So having started your 2D version of Fluent, the first thing you'll need to do is go to the Physics tab, click on General, and we change it to the transient time frame. Okay, next, if we move along to the physics models, it's a thermal calculation, so we need to switch on the energy equation here. And then we can activate the solidification and melting model. In this release of Fluent, so this is 23R2, you can do that by clicking More, and we'll get our drop-down box here, and you can see you've got all of the additional models. So solidification melting is here, so let's just click that. And first thing is switch it on by checking this box here, and then we move over to parameters. There's one parameter that you have to enter. It's called the Moshi zone parameter. This is essentially, it's like a damping factor. The larger that value is, the faster the velocities will go to zero as the material solidifies. Okay, so the trade-off with this is that if you increase it, then you're going to get the solidification velocities happening much faster. But there'll be a point where if that parameter is too large, you can introduce some instabilities into the calculation. So you may have to do a little bit of experimentation there, gradually increasing this and maintaining solution stability at the same time. The recommended range here is 10 to the 4 to 10 to the 7, so somewhere in between there would be a good starting point. Okay, so once you've set this, we click OK. And we can then move on to setting up our material properties. And with it being a melting solidification problem, we have a few more properties to enter. So I've created a new fluid material here, called it wax. And I've entered a polynomial for density. So let's just take a look at that. I've used two coefficients, and that's my density versus static temperature. Okay. Specific heat, thermal conductivity, viscosity, all of these are constants, so enter those. And then the last three, these are material properties specific to melting and solidification. So you've got your pure solvent melting heat, which you need to enter, and then you've got your solidus temperature and your liquidus temperature. So the melting is going to occur between these two values. Okay, so once you've entered all of this, you can click Change Create. I've already got this set up, so I'm just going to click on Close. Okay, and then we can move on to setting up our boundary conditions. Now in this model, this is very simple. We've just got two boundaries here. So if I click on Boundaries, I've got the tube inner, and we said that was going to be a constant temperature. So I've got my boundary condition dialog box here. If I click on Thermal, choose temperature, and I'm going to set that to a constant 120 degrees Celsius. Okay, and then we've got the outer boundary. Okay, let's open up the dialog box. Again, go to thermal. We said this would be adiabatic, so I've just selected heat flux and set that to 0. Okay, so that's my boundaries set up. In terms of cell zone conditions, the only thing that you really need to check here is that you have your appropriate material set for the cell zone. In this case, we've only got one, so it's going to default there. But if you have other materials in your database, you just need to make sure that that is set to the the melting material, in our case, which is called wax. Okay, so next we're pretty much ready to run the simulation now. But before we do that, we need to consider the solution methods here. So if I click on methods, I'm actually using the piezo scheme here, which is recommended for transients, and then under the spatial discretization, I've got least squares, standard for pressure, and then second order for momentum and energy. When we initialize the solution, I'm using standard initialization because basically the starting point of this simulation is that really nothing is happening here. You've just got a wax solid material. Okay, so my gauge pressure is 0, my velocities are 0, and I've got to set a temperature which is below the value at which the material is going to be melting. So I've just set that to 48 degrees. So that basically guarantees that this is solid. So if I initialize, okay, so the solution's ready to run. Before I run it, I'm going to create a couple of post-processing objects. So I've got a contour here. So let's just go to edit. And with the solidification melting model, you're able to access those variables here. So if you select it, you can see that we've got liquid fraction and contact resistivity. We're going to look at liquid fraction. So that's going to tell us where the liquid front is. So if I just save and display that, okay, you can see that it's 0, which is what we would expect as the entire domain is solid. I'm also going to set up a volume monitor, which is going to tell me the liquid fraction, and I can plot that as the solution is calculating. Okay, so to do that, we go to definitions. You can click on new volume report. We're going to do a volume integral. Okay, again, pick the field variable, liquid fraction, pick the cell zone. Now you can write that out to a file or plot it. In this case, I'm just going to plot it here. Then you just click OK, and that's your volume report definition set up. Now I've already got one set up here, so if I find that in the table, report definitions, there it is, volume monitor 1. There we go, that's already set up for me. Okay, before I run the solution, I'm also going to create a solution animation so that we can see the liquid front progressing as the simulation proceeds. Okay, so if I look at my calculation activities, you can see I've got my animation set up. Okay, so that's my contour. I'm going to store it in memory, and normally I just do a quick preview here just to make sure that that's set up okay. All right, and now we're ready to run the calculation. So press the calculate button, and this is my volume monitor here, so that's telling me the liquid fraction, and you can see that's gradually increasing as we would expect it to. My residuals are nice. And this is my animation. So you can see the liquid fraction is gradually expanding radially outwards from this heated wall into the solid fraction. Okay, so let's just check on my volume monitor. It's proceeding nicely. Residuals are okay. Let's go back to the liquid fraction. You can see that's behaving perfectly well as we would expect. So I'm just going to let this complete. It'll be a few moments to get to 100%. The other aspect of this is you can see that I'm using a time step size of 1 second here. Again, that is very much case dependent, so you would need to sensitize that as well. Okay, calculation complete. So you can see that my liquid fraction is gradually increasing, and let's just have a quick look now at the animation. So if I go to results, animation, solution playback, and there we go. You can see the liquid fraction and the melting front in our model. Okay, so that was a very simple demonstration of the solidification and Melting model in Ansys Fluent. I hope you found this useful, and thanks for watching.